discussing a very interesting topic that was known as the fuzzy inference system. We delved straight inside what the fuzzy inference systems were, unless of course that there were time constraints because of which we had to stop right before discussion of the fuzzy operators. They were into the next level of abstraction, going deep into inside the paradigm of fuzzy inference systems. Now, one thing that we introduced in that hour of lecture was the membership functions, and of course I said the fact that there are numerous kinds of membership functions. I did not explicitly state them up. So even before coming here, I have done this little bit of homework over here where I stated down the numerous kinds of membership functions that are normally used. The first one, of course, it's like a generalized, the bell-shaped membership function. It represents a reciprocal relationship. These are what the parameters that I can probably control, and then if I draw it up graphically, it comes up to be a nice little bell shape in nature. And that is what we know, that if this is an x over here, this is what would represent the mu x over here. If this is my input variable over here, this is what will denote its membership, that can range anywhere between 0 from both the extremes to 1 right at the top of the bell. Of course, more or less it looks like a Gaussian curve, apart from the fact that this would be a bit more flat in nature. And of course, why do we exploit this kind of curve? It's something that you can get when we delve straight away into the problem domain. That is when we know that sometimes we may need to adapt the membership function to somewhere, and that is what becomes very handy. And then of course our very own Gaussian membership function, we've used it numerous times, a very popular curve. Sometimes when we don't have anything, then we say that let this function be Gaussian in nature. We do not know how to model a problem. We say that let us assume this to be Gaussian in nature, and more or less it works. Because the various membership functions that we have got over here, they can be pulled, they can be pushed, they can be expanded, contracted, and all sorts of things by these control variables. And that is where we can adapt any problem to any situation. Using these control variables, we can make them perform really well in nature. And of course, when I say that we can make them perform really well in nature, it not only means that we need to tune in these membership functions, it also means that we can tune the various rules that would be fired, the various modeling of the inputs, the number of membership functions, and all those things. So the playground is really big. The playground in which we operate is really big. That has its own advantages and disadvantages. Disadvantages in the sense that since it's a bigger playground, I would need to tune in a lot of parameters to get the optimal performance, and I can never be guaranteed that the performance is optimal. And it's good in such a way that even if I do not perform well on some grounds, I can overcast its negative effect on some other grounds, and I can get overall a good performance. So that's where Gaussian is like one of the most conventionally used function. Many of the known phenomena, they are known to be Gaussian in nature, and that's why we use a lot of Gaussian into all our system modeling. Now this is what is the sigmoidal in nature. This is what is a sigmoidal curve. We get some very fantastic curves when we try to unite two sigmoidal functions. So this one sigmoidal is the other. The sigmoidal, what I'm referring to is that differential sigmoidal, that again has more or less the same kind of curve out over here. Numerous things that it can represent. And again, I've got more controllable parameters to play around with. All A1, A2, C1 and C2. These represent nothing but the centers over here, and A1 and A2 the expanse over here. So I've got a lot to tune in this parameter, and again it's like a wonderful curve that it can be used for representing many of the curves. And similarly, when I don't take in the difference, I take in the product, and I call that the product sigmoidal. Again, I can play around with, so it's a beautiful curve that on the same lines that I can draw, all used for system modeling. Now, of course, the actual number of curves can be much larger than that. You can use any kind of mathematical formulations. We did not use some very simple ones. those could have ranged between 0 and 1 and could have really modeled up well, except for the triangle, of course, that represented linear relationship. There can be numerous membership functions that we can use for modeling of a problem. And of course, we'll only be able to model the problem if we know how the input variable behaves and what are the trends and change of membership functions that it behaves. Some part of it we might try to discuss in the application domain, some part later out in this hour of lecture, and some part, of course, most of it we might not be able to discuss since that is the specialty of the soft computing system design, where the work is entirely to design all these membership functions, design all these rules, and the other part of it is, of course, conventional in nature. What can be done by any person and how do we use these systems for problem solving. So this was a product sequential, and similarly we have something called as an S-shaped, which would be nothing but a kind of an S drawn over here. There would be something known as a Z-shaped, something like this, and of course I can contract, I can go around these based on these control points over here and these control points over here. There is something that is formed from both of them. From a combination of both of them, I use some part of this, I use some part of them, and I get this pie shape. So this is what is S-shaped. This is what would be Z-shaped. And this would be pie-shaped. A combination of these. And again, we get more possibilities of how we can play around with. We get tremendous kinds of possibilities in which we can work over all these kinds of membership functions, and all of them being used for some kind of problem solving into our everyday work, into whatever system that we are trying to model. Again, because it's fuzzy, using some kind of rule base, using some kind of production rules used in a fuzzy sense. So that's probably all that I will speak about the membership functions. Again, to repeat that normally we do not try out all the various kinds of membership functions. We do not try whether S-shaped is better, P-shaped is better. If we have some kind of initial idea regarding how the input behaves, we use a specific membership function as per our idea, or else we just take, might be a triangular in nature, might be a Gaussian in nature. The most simple thing that you can do out is take these kinds of membership functions, where this becomes the minimum x, this becomes the maximum x, and this is what the max value is there. This is what can be the most simple form of it, and these systems work. They work flawlessly. They work, of course, it's soft computing, so I cannot say flawlessly, but they work very well. And this would be normally what very common choice of curve. Or I can make these Gaussian in nature, so there will be some curvish nature to the same curve. And again, the Gaussian curve also works finely, it works very well. So that is normally when we do not have any preconceived idea regarding the input, we might, as a black box approach, say let these be the membership functions, and I will try to adapt to the rules much better. I'll try to make a much better kind of rules for the entire system. Now we move on into what was exactly our point of discussion. When we were into our previous hour of lecture, we'll move entirely from membership function, we'll move entirely into that domain, and those were the fuzzy operators. Where in the previous hour we've already seen that we first study mainly three operators, and, or, and not. The first one would be the and fuzzy operator. Now again, when I say the word and, we have studied this operator numerous times. So let me again say that a fuzzy operator and is nothing but a logical operator. What it does is, it does the task of combining two conditions. So condition 1 and condition 2, and give in an output. So I draw in a truth table for and. So if I say there's x, there's y, there's x and y, what we have already learned is the truth table comes out to be something like this. If both the conditions, if any of the conditions is false, the final result comes out to be false. If any of the condition is false, the final result comes out to be false. If any, both of them are true, then the final result comes out to be true. So if I say, if the road is bad and it is raining, then drive carefully. So when both these conditions would be true, then only I need to drive carefully. So let me again take up the graphical example that we had drawn the previous time. Let me say that at any state of time my x is nothing but this. This is what is the membership function of x in a discrete domain. I am again talking in discrete domain, the fundamentals of which we have already discussed. So if this was load measured on a scale of 0 to 1, let me say anything greater than 0.7 is 1 and anything less than 0.7 is 0. Let me again take another variable. This was x, let me take it as y. Let me say it was nothing but rain. So I'll have again a degree. Let me take 0 to 50 as its range. I say anything greater than 0.8 over here is high. And that is what denotes my mu of y. So that's what is x, that is what is y. I am asked to compute x and y. I am asked to compute x and y. So I start off from here, 0 and 0 will be 0. Here 0.1 and 0.1 would again be 0. I go up right from here till this 0.7, both these values are 0 and therefore my output is always 0. It's 0 over here, it's 0 over here, 0 and 0 will always be 0 till 0.7 over here. I'll still go further up with it. I'll say .7 to 0.8. This is 1 over here and this is 0 over here. 1 and 0 is nothing but 0. So there's this 1 over here, there's a 0 over here. 1 and 0 will again be 0. After this 0.8 mark over here, the membership function here is 1, the membership degree here is 1, so it's 1 and 1, and that is when after 0.8 I get a value of 1. And this is what comes up to be the graph of x and y. This is what happens to be the graph of the variable x and the variable y here. When I add these two graphs, this is the graph that I get, and it's again into a discrete domain, into a crisp domain, into a normal sets. What I got is as x and y. I'll just take another example. This was like saying the first one probably denoted the set high and the second one also the set high. So probably the first one could have been said that the road was bad and second one could have been said that the rainfall was high. I taken a moderate of both of these. So let me say it's over here like this, and this is my x. Let me say this is 0.3, let me say this is 0.8, and let me say this is y. Let me say it's 0.5 over here, and here's how it's goes, this is y. Again I apply some kind of and over it. So when I apply and, now both of these are sets, both of these are nothing but sets. This denotes the range of values that belong to the set that I have drawn over here. This belongs to the set of values that I have drawn over here. When I am doing and, I am basically taking and of two sets. and the graph that I am drawing is exactly the set that I obtain. One way to understand. The second way to understand, of course, is the membership value of any value over here. The third way that of course that for any value that I say that what is the membership function, I'll always get either a 0 or a 1, and I then simply using this truth table I find out the membership value of the final result. So if I take AND of these two, what I'll get is if I take an AND of these two, all that I'll get is that till 0.3 both are 0, no problem, my answer will be always 0 and 0, 0. Till 0.5, this is 0, this is 1 and this is 0. Till 0.3 to 0.5 over here, this shows a membership value of 1 and this shows a membership value of 0. As a result, 1 and 0 will be 0, so I go 0 over here, so this is the way that I have gone. I go from 0.5 up to say 0.8. This is 1 and this is 1. Now 1 and 1 is 1. So my value will be 1 over here. I go from 0.5 to 0.8 like this. I continue my journey from 0.8 over here. I go up, this is 0 and this is 1. Now 0 and 1 is nothing but 0. So this is the curve that I get. This is exactly the curve that I get out over here. This would be what is x and y. Now these two scales of 0 to 1 and 0 to 1 were only taken for convenience for us. They were only and only taken for convenience to us so that we can draw these curves well. In reality, this would be another scale and this would be another scale, and that is when I say that again you come up to the set theory. These are two completely different things, and I am only trying to make it a binary relation whether the rule should fire or the rule should not fire. So what this probably meant that if, let me say this was load, if load is moderate and I come up over here, I say rain is high, then something. I'm only discussing the antecedent part of it, I'm not discussing the consequent part of it. And what I'm trying to do by drawing these curves out here, the basic thing that I'm trying to do by drawing these curves out here is nothing but to understand whether this rule should fire or not. If this rule fires, then whatever follows in consequent will happen, the system will change, the state will change. If it does not happen, it will not happen. All that I'm trying to do by doing this curve is trying to find out values of x and y in which the combination of which fires this rule. So again the scales are different, but then I will ultimately concern with the entire scale, the range of values in which this rule fires. And what I ultimately get is this curve out over here, which denotes when all the rule fire. So this was an in the discrete domain. This was what was and in the discrete domain, but this is not what my point of study is. This is what we have already studied in so many times into our normal courses. What we are studying is the fuzzy domain. So I again make in this truth table. This was for discrete set, this was for crisp sets. I make the same truth table but for fuzzy domain. What I mean is that here there will not be any 0, there will not be any 1, there will always be a mu x and there will be a mu y. All the zeros will be replaced by mu x, or ones will be replaced again by mu x. It can take in any value from 0 to 1 and mu y can take in any value from 0 to 1. So in place of zeros and ones I got mu x and mu y. All that it says is that whenever you are trying to take an and into a fuzzy domain, it would be nothing but a minimum of mu x and mu y. This is the first type of function that is used where I use the word minimum, the second that is used is product. This is the second equation that is used into our fuzzy domain. So whenever I enter into the fuzzy domain, I'll model and either by this or by this. Now that very well means that my entire system can either be minimum driven or it can be product driven. I can either have a minimum driven system or a product driven system, so the entire kind of modeling, it bifurcates into two parts. The entire system I can model using a minimum or a product. This is called what is called as the minimum, and this is what is called as the product. So again, what I said that 0, 0, 0, I made in these kinds of truth table. Let me again make in this kind of truth table for the fuzzy sets. Of course, the sets are continuous in nature, so I can have anything like 0.1, 0.8, x and y would either be 0.1 if I go by the minimum, or it can be 0.08 if I go by the product. This was what is min and this is what is product. Again, let me take 0.5 and 0.5. It will be nothing but 0.5 if I take minimum and 0.25 if I take product. Let me go in for 0 and 0. It will be 0 here, 0 here. Let me go in for 0 and 1 over here. It will be 0 here, 0 here. Let me take 1, 0 here. It will again be 0, 1, 1. It will be 1 over here. Minimum of 1 and 1. And product of 1 and 1 is always 1. Now this is nothing but minimum. Minimum of 0.5, 0.5 is 0.5. 0, 0 is 0, 0, 1 is 0, 1, 0. Minimum is 0 and 1 and 1. Minimum of 1 and 1 is 1. And this is product 1 into 1, 1, 1 into 0, 0, 0, 1 into 1, 0, 0 into 0, 0, and 0.5 into 0.5, 0.25. So by these four relations, I get in one very good thing, I get in one very good understanding that my fuzzy sets are obeying the laws of the discrete sets. This is exactly the truth table of and by both these modeling systems as was in my discrete sets. So whatever laws are held with discrete sets, they are obeyed over here. And that again should not differ the point that all the cumulative laws or the associative laws and all those kinds of laws that AND obeys, this thing will also obey all those laws. It can be verified simply by the simple mathematical equations where you replace AND by the minimum out over here or the product out over here. Both these operations, they have the same laws as the AND binary operator, as the AND crisp operator that we have been studying in Boolean algebra. It has exactly the same laws that it follows. And of course, I can make this truth table as long as possible. 0.005 and 0.9, that will be something. 0.05, 0.001, that will be something. 0.8, 0.005, that will be something over to both these domains. Whenever I make in any system, I will make a very hard choice between this or this. I'll make it a very hard choice between either of these, but then always I use one of these two operators. Let me very quickly come up into the same example where this time I plotted the same two curves that I drew the previous times, one representing x and mu x over here and the other representing y and mu y over here. Let me draw exactly the same curves. Let me take one of the case as this. Again, it is continuous in nature because now I am drawing fuzzy operators. I am drawing some kind of fuzzy operator, so it's much more continuous in nature. And let me say that my y was nothing but this time I will try to draw it in a different fashion. Let me say it was, I am trying to draw it like this. It will give me, min will give me a curve. Min will of course give me a curve. And that is when I go point by point. I start from here till here, this is minimum, till here, this is minimum, till here, this is minimum, till here, this is minimum. And as I go up over here, I guess this is always lesser than this, so my curve will be exactly as was this. I am assuming that in its y value, this never goes this, and it's quite an easy assumption to make. I'll draw these grid lines for the sake of clarity. This was always lower than this in terms of y value. So they all started from 0, it started rising, but then I take minimum of this and this, which is nothing but this. I go up over here, minimum of this and this is nothing but this. I go up still here, minimum of this and this is nothing but this. It will be exactly the same curve. This was when I take the min operation. If I take in the product operation, the graph will be slightly different. The graph will be slightly different if I take in the product operation. 0 into 0 will nothing be but 0. So till this time operation is almost 0. Till this value is almost 0, it will be 0 over here. Now I have two membership values to multiply when I come after this region. If I go anywhere after this region, I got two probabilities to multiply, I got two membership values to multiply, and whenever I multiply two membership values, I always get in a membership value that is lesser than both the membership values. Now remember, any number less than 1, if I multiply by any number less than 1, it will always reduce. So that's why my curve in product will be something like this. Towards the end, both reach a value of 1. So towards the end, I'll just reach in a value of 1. So this will be nothing but a sliced down version of this. It will be a sliced down version of this. This region, it reaches 1. So 1 into this curve over this region over here will almost show me this curve over here that I've drawn over here. So this region will be almost intact. But towards this region is less than 1, that's why it will suppress its value, and that's why I get in a diminished version of this curve. That is when I use the product. A better example would be when I take in some middle values. I take in x to be like this. I take out y to be like this. I'll draw the min first. 0, 0, it will start from 0 again, it's almost 0. This has started to rise, but then a minimum of this over this region, and this over this region is nothing but this itself. This is rising, but still the minimum is over here. This is rising high, but still the minimum is shown by this curve, and so on. This is rising, but this is on the downfall, so I'll get curves on this order. Once this reaches its maximum, this has the same value over here. This has reached its maximum, but I am taking the minimum of these, but this has taken the same value. I go up to the point over somewhere around here, where the curve is nothing but this point over here. Now this is sharply falling, so at some point of time, this will overcome the rise over here. That's why I get in a downfall over here. I'll get in some kind of downfall over here because I'll use this kind of trends over there. I'll be going by nothing but these trends over here, and after that, this is rising, but this is falling. So minimum of these two is nothing but this curve, so it will come up almost over here. And at these 2 points, both these are 0 and this is 0, so this will be nothing but 0 and 1, and by the min operator. It will be almost some kind of curve over here. Again, what you might expect is this would be a steep curve like this. Because till here I was following this curve, and till here I was following this curve. And suddenly I started following this curve. Because the value of this had been lesser than the value of this over here, and therefore the curve would become very steep out here. So I'll get this cool kind of thing over here. Again, normally when you plot in all these curves of any variable over the other variable, you get in the functions automatically. Similarly, I can draw a fall from the min to the product. Again, I will take in the pointwise product of both of these. It will follow almost the same curve. It will follow almost the same curve. When I take in 0 into 0, it becomes 0. This is high, this is low. So the overall value will be much lower than both of these. It will start, this increases right here itself, but the value of this is low, so I'll have a slow increase over here. When it reaches 1, it will show exactly the point over here, because a membership value of 1 into whatever membership value is here or out here at this location, it will show me entirely this location over here. Now this will fall and this is rising. This is falling and this is rising. I will conduct again a point-wise product. I will contain a point-wise product of these two values, and that is where I will get in my product again something like this. Again, towards the end, both of these are 0, 0 into 0 becomes 0. So that is entirely what is there into the fuzzy world. The actual curves of it, of course, are very simple to draw. You can draw it using Excel, you can draw it using any of the graphical tools that you use to plot graphs. Assume two membership functions and just take the point-wise product of both of them, or the point-wise minimum of both of them, and you will get in all these three graphs. Now in this AND operation, one thing that we have seen is that they behave, all the laws behave by the discrete crisp sets. The second thing that we saw is that how we conduct a pointwise addition, pointwise multiplication over the entire membership function graph, and we get in a graph. How we conduct a pointwise multiplication, because there are two conditions written, we are ANDing it. So the first condition represents a curve of its own, the second condition represents a curve of its own. For the various values of x and y, we are interested in how can we get the various values of the curve that results from both these curves. One thing important is that why is it that a min and a prod, they solve a problem? How is it that min and prod, they solve a problem? So for the product, let me again take a deep into the probability theory. Let me go a bit into the probability theory, because fuzziness is nothing but the degree to which a membership an element belongs to sets, or the probability of an event happening. Discrete sense says that the condition is true or false, and fuzzy sets, they represent the probability to which the condition is true and the probability of which the condition is false. So what God says is that there is an, let me say that there is an event E1 and there is an event E2. E1 happens with a probability P1 and E2 happens with a probability P2. The probability that both these events, they happen one after the other, considering independent events, is nothing but first event happens into the second event happens, so that will be something like P1, P2. This can exactly be represented as what we have it as the fuzzy membership functions. This can what is the fuzzy and the product of two independent variables. The first condition was true with the probability P1, the second condition was true with the probability P2. From the probability theory, that the resultant condition will be true is nothing but both conditions independent, P1 into P2. And we know that if we take P1, the condition, the probability that the first condition proved to be nothing but its membership value mu x, and the probability that the second condition is true to be nothing but mu y. I am just replacing the word probability by the word membership, then I get what is my fuzzy AND. So again, there is an application of nothing but the probability theory in how this product has been modeled. Min is again from the same theory. I say that there are two gates to something and I need to break both of them in order that I get into what lies after it. So I need to break in both the gates. Both the gates might have some kind of capability that I break them up. They might have some kind of capability that I break them up. They might have some kind of probability that they won't get of security. They might have some probability of them being secure. Now what I need to assure is that I possess enough capability to break the weaker ones of them. If I can break the weaker one, I can always break the stronger one. If I can break the weaker one, I can always break the stronger one. That means I've got capabilities in excess. here somewhere assume that both those have some kind of same kind of capability of breaking. So if I can break the weaker one, I can of course break the stronger one. All I need to assure is that I need to have capability more than that. So in some sense, if I see it again from the probability theory, that the probability that the gate gets break is that if the weaker gate gets break, that means I'll choose the minimum of them, I'll choose the minimum of the capability, I'll choose the minimum of probabilities of breaking of both of them. I'll then, using my capability, break up the door with the minimum probability of being broken. If I can break this one, I can obviously break the other one. So that's what more or less is the application of an operator. If I can break the door that is minimal probable of being broken, I can break the other doors very easily. I always have the capability larger than that. We have exactly the same kind of treatment for the other fuzzy operators. Of course, because the treatment is exactly the same, we need not repeat much of the discussion. The underlying fact is the same. In place of the antecedent, in place of it being if condition 1 and condition 2, it will just change if condition 1 or condition 2. So we have a truth table for the or. I'll have x, y, I'll have x or y, which is nothing but 0, 0, 0, 0, 1, 1, 1, 0, 1, 1, 1 and 1. If any one of these conditions are true, my output is true. If any one of these conditions are true, my output is always true. I can have a discrete realization of them very easily. I'll draw in something like this, I'll draw in something like this, I'll get in something like this, 0, 0, 0. After this gets 1, this gets 0, 1, 0, 1. Till here, this is 0, this is 1, so output is 1. After whatever follows in this region rather, this is 1, this is 0, so the output is 1. Here this is 1, this is 0, the output is 1. And here this is 0, this is 0, so the output is 0. So this can be what it can be mu of x, this can be what is mu of y, this can be what is mu of x and y. Mu of x or y rather. And similarly, I can trace up, I can formulate a very simple kind of definition for the fuzzy or. I can have some very kind of simple definition for what the fuzzy or is all about. I say that x or y is nothing but, again, I will not write one equation, I will write two equations. I can use either one of them. There are two ways in which OR is modeled in the same way that there were two ways in which AND was modeled. So my one modeling of OR, what it says is that it is nothing but a maximum of x, or rather mu x and mu y. There it was minimum, here it is maximum. A minimum gets replaced by a maximum. And the other, it says it is nothing but mu x plus mu y minus mu x mu y. This is what is known as the max condition, and the condition and the second modeling of it is what is known as a probabilistic OR condition. So I've got a max definition and I've got a probabilistic OR definition, and based on both these definitions is where I actually work upon. Either things would be by application of max, or things would be by the application of a probabilistic OR. And I use either one of these in making the system. So let me again very quickly come up onto the fuzzy domain of what I actually drew. And let me again take in a simple example. Okay, by the way, if I make it an OR table of x and y over here, if I call it as my fuzzy OR and this is x or y, I can again take in simple example 0.1, 0.8. By the max, it will be nothing but 0.8. And by my probabilistic OR, it will be nothing plus 0.1 plus 0.8, that will be 0.9 minus 0.08. So that will come out to be 0.88. That will be what the probabilistic OR. The important thing is 0, 0, 0, 1, 1, 0 and 1, 1. Maximum of 0 and 0 is 0, maximum 0, 1 is 1, maximum 1, 0 is 1, maximum 1, 1 is 1. That is what exactly is my equation when it comes to the application of a discrete OR, where membership values can be only 0 or 1. That is exactly what comes out to be my equations out in this case. And again, if I apply probabilistic OR, 0 into 0, 0, 0 plus 0, 0 minus 0 into 0, that will come out to be 0. 0 plus 1, 1 minus 0 into 1, that will come out to be 0, so this will be 1. 1, 0, 1 plus 0 is 1, minus 0 into 1, that will come out to be 1. And 1 plus 1, 2, minus 1 into 1, 1, so 2 minus 1 is nothing but 1. So my max of x or y and my x plus y minus xy, they both obey my discrete logic, they both obey my discrete OR, they both obey my Boolean OR, and what can be verified by application of both these. I am not going to the formal proof of it, it's rather very trivial. All the associative, cumulative, distributive law obeyed by my and my OR, my discrete and my discrete OR, they would be obeyed by my fuzzy and my fuzzy OR as well. They can be very simply verified. So again, let me quickly draw about let me say this is my x, this is my y, I'll simply take in a maximum of both of them. From here this rises, so therefore I'll follow this curve. Again this is rising, this is by the application of maths. I'll follow this curve till it rises up over here. After this is rising and this is falling, so I'll follow this curve. And again this is always larger than this, so I'll follow this curve. This is what will come out to be the max. Point by point comparison can be done, point by point comparison can be made. So that is what is by application of max operator. That is what exactly is the application of my max operator. I'll have in my probabilistic OR operator that will behave almost in a similar way, except for the curve will be much more smooth in nature, where it tries to capture the maximum of them. The actual curve, it can be very easily drawn, wherein I can take point by point points over both these domains. I can take up the entire set of points over both these domains, and I can have in a kind of curve that combines both these curves using an OR operator. So this was and that was OR. Realization of and, we took it from the probability theory. So let us again take up realization of OR from the same probabilistic theory. Let me again take in the probabilistic theory to analyze how OR behaves. I'll go over with this one. Two events P1 and E2, they happen with the probability P1 and P2. There are two events P1 and P2 and they happen with probabilities P1 and P2. I am asked what is the probability of any one event happening. Either event 1 happens or the event 2 happens, and that I know is nothing but the probability that E1 happens or E2 happens is nothing but the probability that E1 happens with the probability that event E2 happens minus the probability that both of them happen. So that is P1 plus P2 minus P1 into P2. That is what the net probability comes out to be, as in this case. That is what is the application of the probabilistic OR. Sometimes we even call this as a OR. Again, let me say that there was something over here I needed to get here. There were two dots, this time in parallel. The other time they were in series, this time it's parallel. They both, I am here, I need to cross the sun up. Here I'll try to break in the dot that is more easier to me to break. I'll select out one of these two dots, that is very easy to break. So the probability of breaking is very high. I'll select one dot, the probability of breaking is very high, I'll simply break that dot and I'll go open. So from the same probabilistic theory we say that if P1 and P2 are the two events, whatever is the maximum theory, whatever is the maximum of both of them, I'll simply break that very dot. So if this door is easier to break, it has got a higher probability of being broken, I'll simply select this door and I'll break it up. So the application of max is what it does. So that's what is the application of max over here. So and it was if event E1 happens and event E2 happens. So with the probabilistic theory, we multiply both of them here. It's event E1 happens or event E2 happens, and what we get as a probabilistic or equation, a very famous equation that simply says P1 plus P2 minus P1 P2. What it can be represented as mu x plus mu y minus mu x mu y, where nothing but probability has been changed by the work of mu. The next operator that we have got is what is known as the NOT operator. Again, from simple Boolean algebra, we know that NOT is nothing but a unary operator, so it just flips. If the input is x and the output is not x, 0 becomes 1 and 1 becomes 0. That's what we all know. And again, the complementary law, we know that NOT and NOT of x is nothing but x, and all those laws that NOT behaves, all those are intact, that come right from the Boolean algebra. The aim of fuzzy algebra is not to replace the Boolean algebra, but the aim of fuzzy algebra is that it can add some kind of fuzziness into the Boolean algebra, where the conditions may be true to some degree, to some probability. So again, if we have got an x like this over here, if I have got mu x over here, I have got x over here, not x is nothing but its converse. 1 becomes 0 and 0 becomes 1. It gets flipped. This gets rise and this gets low. And the same equations that follow. Exactly the same equations that follow. The aim is that if you can only construct the counterparts of it. What NOT of fuzzy x, it simply means, a NOT of fuzzy x, it simply means that I take 1 minus mu x. A NOT of x would simply mean I take 1 minus x, and that is exactly what my equations are. So if I have got x over here and I have got not x over here, if x is true to 0.8, not x will be true to 0.2. If x is true to 0.1, not x will be true to 0.9. 0 becomes 1 and 1 becomes 0. So all the complementary laws are intact if I model this in this way. And the fuzzy theory is that the fuzzy counterpart of it is exactly as simple to draw. If I've got mu x over here, I've got x over here, something like this. This gets nothing but something like this. 0 becomes 1, 1 becomes 0, and the curves flip. The curves exactly flip. It's like seeing it from the upside down. If I got something like this over here, this would be as simple as something like this over here. So the entire curve flips. With nothing but it takes in a flip. Round about 0.5 membership value, it flips. 0.5, it's known that by the application of NOT operator, a value of 0.5 will be 1 minus 0.5, that will be nothing but 0.5 over here. And the realization is again very simple. Realization of NOT is very simple. If there is an event E, that E1, that happens with a probability P1. Let me say that there is an event E1, and the probability of happening of this event is P1. So what is the probability of this event not happening is simply 1 minus P1, and that I can say is 1 minus mu of x. Into the condition part of it, of course, what we have done is that earlier we took in condition like if x and y, if the condition x and the condition y, in all we took if the condition x or the condition y, here we are saying not. Here we are happening if not x, that is if x does not happen. That is what exactly the condition is being dealt out over here. So this was what was the basic three operators that we get while solving the antecedent part of it. The AND operator, the OR operator, as well as the NOT operator. These are what are the basic three operators. and we can solve the entire antecedent of any equation by the application of these three operators. Again, should not be required to be discussed that you have any condition. First you solve the not part of it, so that is when all the nots are gone. Then you solve the and part and the or part using all those associative laws. So if I am given any problem, let me take in a kind of fictitious problem here. If not raining and not sunshine and road is moderate, let me say, and again temperature is high, then something. I'm only concerned about the antecedent part of it. Let me say that my fuzzy set was, it was raining to the, at any particular day that I observed, raining was to the extent of 0.8, sunshine was to the extent of 0.2, road was something like 0.7, and temperature was as high as 0.1. Let me say this is what was the recording of one day. I'll basically use something like not raining is high over here and sunshine is low over here. I'll have to associate them up to some membership functions, and these two are fine. So temperature in its high count for any day had in showed a membership of 0.1. Temperature shows a membership of 0.1 to this membership function high. Road shows a membership of 0.7 to this membership function called moderate. Sunshine shows a membership function of 0.3. I said that if I consider rain over here, there was something as high. A membership function was there. It was, let's say, raining 55 centimeter over here. What can be maximum of 100 centimeters over here? And this is what gave me 0.8 value when recorded for this membership function called as high. Similarly, I'll get for all these membership functions. This is what was one recording of it. So if I solve this, I can, first thing that I've already done is that I've taken out the membership value of rain for the membership function high. I've taken out the membership value of sunshine for the membership function low. I've taken out the membership value of road for the membership function moderate, and so on. This is what I've already done. I say if not raining is high is nothing but 0.8 and sunshine is low is nothing but 0.2, and there's a not over here, and road is moderate is nothing but 0.7 out here, and temperature is high is nothing but 0.1 out here. I solve this further. Not 0.8 is 0.2 and not 0.2 is nothing but 0.8 and 0.7 and 0.1. Let me say the problem modeling was such that I was using min. 0.2 min 0.8. And 0.7 and 0.1. This will be nothing but 0.2 and 0.7 and 0.1. I am following the same Boolean algebra laws. Please accept the fact. This will be minimum 0.2 and 0.7. This will be nothing but 0.2 and 0.1. It will come out to be minimum 0.7 and 0.1. So the value of this antecedent is nothing but 0.1, and this denotes the probability of this rule being fired. This rule will be fired to the extent of 0.1. That is all that we have achieved using these three basic operators of and, or, and not. Any rule we can solve the antecedent part of it, and we can come to know to what degree this rule gets fired. The next part, of course, is the consequent part of it. That is what we'll be dealing in the next hour of study.